Good morning. Welcome to Krishna's classroom. We continue with the discussion on Riemann series integral. We pick up from where we left last time and then look at some interpretation of the vector valued integration. That is a context in which possibly you come across this in a physical situation, and also look at an application of the Riemann series integral of vector valued functions. Now, this is our plan for today's lecture. So we begin with the physical application. So it's a situation in dynamics. What we look at is a velocity vector field is given. So let us consider R2 or R3. Let me take R2. Now, if a particle is moving along a path, along a curve, the situation is this. You have a bee just flying around. Then it traces a certain curve, and that is the path of the bee. And this is technically called the trajectory of the particle, or the trajectory of the object. Now, this corresponds to a change of coordinates in space with respect to time. Therefore, there is a time interval, say something like A to E. This is the time interval, and corresponding to each moment, there is a position in space that the particle occupies. Let us denote this by x, a vector value map. So this is x. So xt has three components now. So x is a map from the t interval AB, that is the time interval AB, to R. Now, it is quite easy to see that x derivative, what x derivative stands for? X derivative stands for the following: dx1 by dt, dx2 by dt, dx3 by dt. We are assuming smooth functions so that the derivative exists and they are continuous. So that much comfort let us ask for. Then you see that x prime is also a map from AB to R. And you see that this x prime at the point xt corresponds to what is called the direction ratios of the tangent vector. In fact, it gives the direction ratios of the tangent vector at the point x. So tangent vector at x. This is the geometric interpretation. Now what about the dynamical interpretation? If you consider what I call C, if C, the semaphore xt is the trajectory of a particle of an object moving in space over a time period, time interval, then x prime t gives the velocity object at this point. So we can denote this by V2. Vt. So Vt equal to that's the velocity. So what you have is V1t, the component. Suppose Vt equal to V1t V2t, then we have dx1 by dt dx2 by dt dx3 by dt V3. So the problem now is the following. Suppose a function, a vector valued function on t is given as v. So you are asking for the following. If a particle is moving with velocity during the time interval a to b with velocity v, which is given, then what is the path of the particle? So the situation is this: v is given, that is, the velocity is given. Well, the question is, v is a function of t. Over an interval a, and the time interval. The question is, what is the path of the object moving the velocity this is the question. Which means you just don't know x1, x2, x3, but what you know is v1, v2, v3 in the set of equations. But it's a very simple situation. v1, v2, v3 are simply functions of t only. That is, it varies with the time only. It does not depend on the space at all. There is no complication of that kind involved. So now you see this is a first order system of equations. So you have the equation this is what you have. Now you know that to fix a solution you also need an initial data. So let us assume that equal to x at a equal to 0. That means it starts from the origin. Okay. So what you have is starting from the origin, which is 0. It starts from the origin. Now what you are asking is this: at time A, the position is given as the origin. Now we want to trace the movement of the particle subject to this restriction. That means its velocity at a given time is the given vector valued function. Okay. So you see that from our knowledge of differential equations, now it's quite easy to know that for the theory of initial value problems there exists a solution. Now we are also taking the function u to be reasonably good in the sense it's just continuous. Let us take it to be continuous. Okay. So what happens in that case? Geometrically, the curve would start from 0 and trace in space. But it starts off along the direction VA. Okay, it starts off along the direction VA and then proceeds further. So once it starts moving, I mean, it cannot be any further influence because it is going to take the path governed by V. Okay. So over the interval, when it reaches the time t, it would have traced the path and then say something like this, say. Then this is the time at this is your. So you want to find out xt. So what you know is at that point the velocity is. So the vt changes as you move from A to B. Okay. What is given is vt. You are asking the question, what is the path traced by this? If you were to start from 0, so what you have is a very, very simple system of equations. dx1 by dt equal to v1, which is a function of t. dx2 by dt v3. Just integrate it. So simple. Therefore, x1 t equal to integral v1 tau d tau from A to T x to T plus generally plus a constant C1 plus C2 plus C3. Now we have initially started off from 0. That means at t equal to a, x 0, which implies and therefore you have to start working on the integral of this, and that essentially requires you to develop the following: integral a to b and this is the context in which one requires to extend the notion of integration. So at the moment we can work with integration, the Riemann integral. So if the function b is Riemann integral, then you can compute. If b is continuous, then you can compute x bar, so that x bar becomes differentiable at the points of continuity of v, and then you have x derivative equal to v from the fundamental theorem of calculus. So that's the situation, the dynamical situation that you come across, which is again the geometric situation, and you see that the v is the direction. What is given is the direction. Once you start from here, there is a set of directions that you have. Okay, let me make one more remark. Suppose instead of this initial point as 0, suppose if you were to start at some other point, say C. Okay, suppose this is the initial point C. This is the vector C. Then what happens is, again, you will get this as the integral as the initial condition will correspond to C, which in turn will give you C1, C2, C3 will be fixed. So this is essentially, in that case, suppose the initial condition is point of the object is at C. This is equal to C1, C2, C3. Then what you get? You will get xt will be simply integral a to t v tau d tau plus the vector. Okay, so you will have the path, the path will be completely translated in that case. The initial path is something like this. It is completely translated. Okay, so that's the geometric as well as physical interpretation of that path. Okay. So we can consider some interesting examples. Let us consider the following. So we are in R3 and the interval T is 0 to 1, 0 to 2 pi say. To set us for convenience, and what you have is we take V to be defined as, the vector is defined as minus sin t cos t and you have 1. Okay. Right? What is this actually? So here you see that the velocity vector at a time t belonging to 0 to 2 pi is given by minus sin t, cos t and 1. Okay. What we are asking for is what is x? If x0 is given by so it's quite easy to compute this. So what one can compute is just integrate these terms. These are very simple, smooth functions which can be integrated, and you get that x1t will be the integral of tau t, which is equal to sin t, and initially it is plus, sorry, it's equal to cos, and at t equal to 0 this gives you 1. Similarly, x2t equal to sin t and x3t what exactly is this path? So the path that you have is cos t. Now one quickly checks that at time t equal to 0 you are at 1, 0, 0. So geometrically you are here. So this is your 1 axis, 2 axis, 3 axis. So you are at the point 1, 0. Now what happens to this? You see that there are the x1 coordinate is cos t, x2 coordinate is sin t, and you know that they satisfy the condition that x1 square plus x2 square equal to 1. Okay, and what happens is that you see, you can think of the movement. There is a movement in the plane 1, 2 space given by cos t, sin t. That means it just goes round. It just goes round in a circle of radius 1. Okay. Now at the same time, it's moving in the x3 direction with a velocity component t. That means it just moves up. Okay. So what one has is the cumulative effect of this movement is this. It just moves around in a spiral. Okay. So in fact, since we are considering for t equal to 2 pi, this is we go only up to this. And if you want a model of that, probably what I can show you is this one. See, it starts, it's a wire, it's a helical structure that comes. Okay, starts from here and just turns around. So something like this. Something that you have. See, this is a helical structure that you get. See, you get a helical structure. Okay. I think I should stand like this so it's more clear. So it turns around like this. It turns around like this. So you would have seen helical structures. There are some staircases which are constructed in this way. Or you can see a creeper climbing over a tree. It just takes this turn. So in short, what you are having is you have a sort of cylinder here, and on the cylinder, consider the cylinder, and the equation of the cylinder is x1 square plus x2 square equal to 1 with x3 arbitrary. Then what you have is you have a helix starting off from here, then goes around and then turns around and reaches here. Okay. So this point would be that end point is going to be once again 1 0 2. So it goes from 1 0 0 all the way up to 1 0 2. Okay, and at any point the tangent vector will correspond to the given. Now this is a simple example which demonstrates this. I think I'll stop that with it. Okay. So I hope everything is clear to you. Right. Now let me consider an application of the Riemann integration of vector value functions. For that we have to do a little bit of preparatory work. So we introduce or look at the kind of curves called the rectifiable curves. Take the general scenario. So we take R2. Now when k equal to 2, we have the complex plane corresponding to that. Of course, complex plane has more structures than R2. That is there. But you know, as a space, it's you know, R2 with some more structures. Okay. It's a two-dimensional vector space over R. Now, when you study analytic functions, whatever we look at becomes relevant. So let us start with some definitions. You have to be very precise about what we mean by a curve. So a continuous mapping gamma of an interval AB to RK is called a curve in space. In the space R. So the condition that we impose is that it should be a continuous mapping. So gamma is a map from the interval AB to RK. And we assume gamma is so every continuous map from an interval AB to RK, from some interval AB to RK, will be considered as a curve in RK. Now the image is essentially a set of points in RK, but we are not looking at the curve as just a set of points. It's more than that. Because when you have the map from gamma from an interval to RK, it is not merely the image points that you are talking about. Because as you progress from A to B, or in time frame from A to B, if you are moving, then there is a corresponding movement that you trace along the curve. So all these things are there. That's why we say it's a continuous mapping. We look at the curve as a mapping rather than a set of points. So that's just a remark. Now some special cases are, so we shall simply say, this is also a terminology, gamma is a, this is the statement that we make. Also say that gamma is a curve in RK, which means there is some interval AB from which there is a map gamma from AB to RK, which is assumed to be continuous. Continuous in the usual sense is a function of t. Okay. Special cases. The first one is if gamma is a one-to-one map, then it is called an arc. Which means the following. Suppose, okay, let us take R2. Then it is just, suppose this is gamma t. What you have is, there is a t interval A to B and gamma is the map. From here, gamma is assumed to be continuous as well as one-to-one. So here we take gamma is one-to-one, which in turn means that, see, you don't have a situation like this. That means if you are considering this as gamma, what happens is that at two time intervals t1 and t2, which is, so suppose this is gamma A, this is gamma B, then this point corresponds to gamma t1 equal to gamma t2, t1 not equal to t. So gamma fails to be a, so this gamma fails to be a arc. So it's not an arc. So that's something which is to be realized. So it should not be self-intersected. The image points forming the curve should not intersect with itself. Or it should not pass through the same point at two or more different times over the interval A. The second case is that if gamma A equal to gamma B, then gamma is a closed curve. That means something like this. Suppose this is gamma A, gamma B. Then it is called a closed curve. See. Something like this. So this is some point. Okay. That's only gamma is continuous. And gamma satisfies the property that it gets back to the same point where it started. Okay, this is what you call it closed curve. Now, what we want is to look at a curve gamma and try to compute the length of that, okay, using this integration process. So what we do is we take up the curve gamma in space. This is gamma A, this is gamma B, not necessarily an arc. Okay. Could be a closed curve, which could be intersecting. See, for instance, you have the circle can be written as some gamma T okay, equal to closed curve. Now this is the point where it starts, so it is 1, 0 and then traces the path in that direction. So this is another case of gamma, a specific case of gamma. This is circle. Okay, now what one does is the following. See, we introduce, so we have the t interval. The t interval is A. Now we introduce a partition with T0, T1, Ti minus 1, Ti, Tn minus 1. We introduce a partition. Okay. Right, let me use the following notation. X0 equal to A, x1, xi minus 1, xi xn minus 1 xn. Okay. So the partition that we introduce is given by x naught Now gamma is a map from here to here. So you have, say, gamma gamma. Right. So we have gamma A equal to gamma x naught. Then you have gamma x1, gamma xi minus 1, gamma xi. Then you have gamma n minus 1 and gamma equal to gamma. This is the picture. Now we construct a polygonal arc. How do you construct a polygonal arc? Join gamma x naught with gamma x1 by a line segment. Then gamma x2 say, then you join this by a line segment, and so on. Join this by a line segment, join this by a line segment. So we construct a polygonal path, okay, and the polygonal path is obtained by joining gamma x naught to gamma x1, gamma x1 to gamma x2, and so on, gamma xi minus 1 to gamma xi by straight line segments, and then you get a continuous polygonal path, okay. Now for that path, we define the following. Define lambda of p gamma, where p is the partition given. We define this by sigma j equal to 1 to n gamma both are vectors, you see. Gamma xj is a vector in Rk, gamma xj minus 1 is a vector in Rk. So we are in Rk, okay, and this I write as the distance. Okay, for clarity, I write this as the two distance between the points gamma xj minus 1 to gamma xj. Okay, this is the straight distance that you have in R, right? Or the L2 distance that you have in R, right? Therefore, gamma lambda p gamma is essentially lambda p gamma is the length of the polygonal path with vertices gamma x0, gamma x1, etc. Gamma etc. Now what one does is make the partition final. As we make the partition finer, what happens to the polygonal path? The polygonal path gets closer to the curve gamma. Okay? As the partition gets finer, the polygonal path gets closer to the curve gamma. Of AB is made finer. The polygonal path gets closer to the path gamma. Or in other words, the polygonal path approaches, that is, the polygonal path approaches gamma. Just take an example. Suppose this is gamma x naught, this is gamma x1, this is gamma x2, and this is the path that this is the polygonal path that you make. Suppose you make it finer. You make it finer by introducing two more points here. Then what happens? The polygonal path that you cut out becomes closer. So this is the example. So this is, we call this gamma x1 prime, gamma x2 prime. So what I am doing is I am introducing two more points into it and make it final. Okay. So it makes reasonable to define the length gamma. So we define the length gamma by gamma lambda gamma equal to supremum of P you see that lambda P gamma is essentially greater than or equal to 0 by definition. Okay, therefore it could at best become infinite or something like that, but this is the case where the supremum is taken over all partitions P. So supremum is taken over A. Now if lambda gamma is finite, we say that gamma is 55. So this is the important step. what you mean by a rectified curve. Okay, so gamma is a continuous map from A to B, and you compute lambda gamma, and if lambda gamma is finite, then you say gamma is rectified. This is the term that we have. That's the criteria for rectified. The curve being rectified. So in certain cases, one can give this lambda gamma one can as a integral. This is an application. So let us see a situation where one can give this as a Riemann integral. Let us take the theorem which essentially tells you under some conditions you can give this as a Riemann integral. So we prove this for curves gamma which is continuously differentiable. So what it says is that if gamma is continuously differentiable on the interval A to B, then it gives you a rectified. And in that case, lambda gamma can be computed using Riemann integration. So let us write it here. If gamma prime is continuous on AB, then gamma is rectifiable and lambda gamma is equal to integral A to B mod norm of gamma prime T. Now this is the theorem. Where we assume gamma prime is continuous on A. Under these circumstances, we can show that gamma is rectified. And this is the expression that you get as the length of the curve. Okay, let's work it out. Let's do this. Okay. So if less than or equal to xi minus 1 less than xi less than b, then we have norm of gamma xi minus gamma this is equal to xi minus 1 to xi, gamma prime t dt. This is it. All that you are observing is that gamma xi minus 1 is integral of integral xi minus 1 to xi of gamma prime t dt. This is just merely an application of the fundamental theorem of calculus. That's what we are. Then this is less than or equal to. Now you can take this norm inside, and what you get is integral xi minus 1 to xi norm of that's quite easy. So what we do? You have to estimate this. Therefore, one can work out the Riemann integral. So this is lambda less than or equal to integral a to b norm now this is now easy to see from this. If you just sum it up, what you get on the other side will be lambda p gamma. Lambda p gamma is less than or equal to sum it up. So it's a finite sum. You can take the interchange the integration and summation, and you get this as or this integral can be summed up from a to b. So you get this. For every partition, this is true for every P of interval P. This is true. Okay, therefore, hence, what we have is we have lambda gamma is less than or equal to integral a to b so that gets you the inequality in one direction. So we get this through this, and now if you can get the reverse inequality, then you get the equality of these two. Okay. To obtain the reverse inequality, we consider the before. Let epsilon positive be here. Now gamma prime is continuous on closed interval, and therefore this uniformly continuous, and therefore there exists a delta positive such that norm of gamma prime S minus gamma prime T is less than epsilon whenever mod P minus S is less than. So this is what you get. So we use that in work on that. Okay, this is possible because gamma prime is assumed to be continuous. Okay, so this stands for this assumption. Gamma prime exists, gamma prime is continuous. Now we choose a partition P of KB in the usual way. Say P XM such that the distance between xi minus 1 to xi is less than 1. That means the mesh length that you choose is less than the delta that is associated with this particular epsilon. So we make use of that now. Then for P belonging to and for any I, this is what you have. Gamma derivative of P is less than or equal to norm of gamma derivative, norm of gamma derivative at xi plus epsilon. What you get is the following. So you can compute this gamma derivative of P minus this is what we call the second triangular inequality, and this is less than epsilon. And use this. If you use this, then you get this inequality. Okay? Therefore, what you have is this. So you get using this, you get integral xi minus 1 to xi this is less than or equal to delta xi plus epsilon into delta xi. This is just integration. Because this is fixed, xi is fixed, therefore you get this integral computed using this inequality. You get this. From this inequality you get this inequality, and from there you get this. Okay. Therefore, and this is less than or equal to norm of integral xi minus 1 to xi plus norm of integral plus epsilon delta xi. So what you have done is to bring this inside this one. So you have this is equal to gamma prime xi minus gamma prime xi minus 1. Okay. So what one does is this, just split this up into the following. So let me write one intermediate step that will make it clear. Right. Okay. So let me write this. So what I do is the following. So I have this step. From this step I rewrite as norm of integral xi minus 1 to xi gamma prime t plus gamma prime xi minus gamma prime of that. Now I estimate this part. If I estimate this part, this is less than or equal to norm of, I split this into two parts. Integral xi gamma prime t dt plus just like very one for the norm plus norm of integral xi minus 1 to xi this part gamma prime xi minus plus epsilon. Now what do I have? What do I know? I know that this is less than epsilon. Therefore, see, I have chosen the partition in such a way that the distance between xi minus 1 and xi for all I is less than delta. Therefore, I get gamma prime being continuous, and we have obtained delta using the epsilon, and this is less than, the distance between these 2 points is less than epsilon. Therefore, you get this is less than. Norm of integral. Okay, what is this? With this you can integrate. So you get here actually norm of gamma xi minus gamma xi minus 1, and this part is less than epsilon. So if you integrate this, you get delta xi, epsilon times delta xi plus the one that is already there. This is what you get. And therefore, suppose you now sum it up. If you sum it up over all partitions, all intervals, so what you have is that this is, see, we started from here. So we have now integral a to b gamma norm of gamma prime t dt is less than or equal to, this is after summing up over the interval AB, that is all partitions. For each partition you get this inequality, this is less than or equal to this. So we get this less than or equal to what one gets. This is essentially, this term is lambda p gamma, and this will give you twice epsilon d minus. So, okay. So this is the inequality that you know. What have you obtained? You obtained the following. You obtained that integral a to b gamma prime t dt, norm of this is less than or equal to lambda this is what we have obtained. Okay, so this is the inequality that emerges, and you know that this is true for all epsilon. Therefore, what you get? So you get this is less than or equal to, that is integral a to b mod norm of gamma prime t dt is less than or equal to, you take over all partitions, then this is so we get the second inequality in the reverse order. Combining this with the previous inequality, you get hence lambda equal to integral a to b so that proves the theorem. Okay, so that's the proof. Now, before we conclude, let us look at some one or two things. examples. You look at a curve y equal to x square in the xy plane. So you can get over the interval -1 to +1. Okay. So what is this? This is a map from the interval -1 to +1. Here, the space. So you have t square over the interval. There is a value. Now you can compute in this case this one. So what is the length of the curve? The length of the curve can be computed as integral. So hence so this is your curve gamma. Lambda gamma in this case is integral a to b. What is the norm of that? What is gamma prime? This is norm of gamma prime t is, see, this is gamma t. Gamma t is equal to t square. Okay. So gamma prime t is norm of 1 to t. Therefore, this integral becomes integral a to b. What is this? This is equal to square root of just compute it. So I just need to compute this. Similarly, you have the example 2. This is a closed curve. This is the ellipse that we have. 1. And you can parameterize this as gamma t equal to a cos t b sin t, for t become into neutral. Complete. Fifth example. So you can work it out in this way, and then it's a matter of evaluating the interfaces. Okay. Thank you very much. I think I stopped. So that concludes our discourses on Riemann Stieltjes integral. In the book by Google, its Principles of Mathematical Analysis, I have based my lectures for Riemann Stieltjes integral on that topics covered in that particular book, and I advise you to work out all problems given under that section, which will give you a lot of experience and insight into what goes on. Thank you very much.